Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another Commentariat. Today is the 24th of May, 2023. I'm trying something a little different this time. I have selected a few comments to reply to that seem to me to be of particular interest to you as a ham radio operator. And we'll see what we come up with as we go through them. Okay, let's begin. This first comment is from Phil Lewis, and the time is correct. I picked that up about, I'll pick these off the web a few minutes ago. He says, and he's talking about an old video, number 339, about reactance versus capacitance and inductance. Okay, and the thing is that the capacitance and inductance are inherent in the coil or capacitor, whereas the reactance of the coil or capacitor varies with frequency. He says this does shed some light on the subject, capitalized. Obviously, he doesn't like it. But it does not speak to whether an amateur operator building experimental antennas should care about phase angle. Generally not. Whether it is affected by or affects resonance or antenna efficiency, no, not really. And how one might go about adjusting or changing the phase angle, adding or subtracting reactance. Now, generally, when we go for resonance, resonance means that the capacitance and inductance equal each other. Therefore, there is no reactance. And so we have a fully resistive antenna. That is almost impossible to do without a tuner of some sort, because a correctly erected dipole, the right height, everything like that, even when it's the right length, lowest SWR, there's going to be some reactance in there. It just is so. Let's see. I know that by looking at real resistance and a Smith chart, one can correct for impedance, capacitance, inductance mismatches, and an antenna tuner can do that for you. Absolutely, it does. In fact, I know the MFJ auto tuner, the MFJ 993A, which is the one I have, it actually calculates what the capacitance or inductance should be to put it in there. What is missing in my mind is how one can adjust or correct it on the antenna itself to improve radiating efficiency. This is simply the missing pieces of the puzzle for me and other experts I've talked to. Yes, you can adjust the antenna if you want to. Now, what you would have to do generally is add capacitance, which will electrically shorten an antenna, or inductance, which will electrically lengthen it. Some commercially available antennas have lumped capacitance and lumped inductance in various places. If you look at the Butternut HF9V, it is just bristling with coils and capacitors. Other antennas, if you put a piece of something, aluminum, next to the main the main antenna, it will add capacitance or inductance, and so on and so forth. There are all kinds of things you can do with weird stuff, like putting maybe at the very end of it a capacity hat if you want to add some capacitance, and so on. So there are lots of things that you can do, and these are explained in the various antenna handbooks. The problem is, and this is, I think, an insurmountable problem. The problem is that you have to measure the impedance at the feed point to the antenna, which, if you go up there and try to measure that, your presence and the presence of this metal meter are going to change the antenna. It's sort of an example of the Heisenberg uncertainty principle. You can't measure something without changing what you're measuring. Just can't do it. So what some people do is, if they're looking at a single frequency, They use their antenna analyzer to calculate the length of the coax to be exactly 1/2 wavelength, taking into account the velocity factor and so on. Then if you connect that to your antenna and then connect that to your analyzer, what you measure at the end of that half wave or full wave or whatever, multiple of half wave, will be exactly the impedance of the antenna, and then you can try little things to bring it in. Now, the Smith chart does not just start with real inductance. You can start with both your resistance and impedance, and often the newer antenna analyzers will show you a Smith chart and maybe even draw a little circle on it, or you can measure it at a single frequency, because the spot on the Smith chart changes with frequency. So if you're measuring at a certain frequency, it will tell you not only the resistance, but also the capacitance or inductance. Okay, and usually if you try to make the antenna so that it's reasonably in tune, like 1.6 to 1 SWR, which is pretty good for an antenna that isn't otherwise compensated, then you can tweak all that out with the antenna tuner and you're fine. Now, if you are going to build an antenna array, suddenly phase angle becomes important. Some DXers that I've seen put up four vertical antennas, like on 40 meters. They're 33 feet high, and then they space them a certain distance apart. And then you can vary the phasing to the antennas and steer the beam. The problem is it's such a broad beam, no matter how you steer it, that what they usually do is they have a selection that selects one of four quadrants. It is possible to put up more arrays and to phase them to point in multiple directions. A lot of the military's radars, where you're dealing with 10 centimeter wavelength, can phase multiple arrays, different phase shift across them, to point the beam anywhere they want. And because they've got so many antennas, they can point it very accurately in a nice tight little beam once you get out past the near field. Okay, so you can match. Now remember that the Smith chart is a transmission line calculator, okay? And what you are seeing when you're looking at the station end of your transmission line, if you're getting the Smith chart there, you're getting the combination of the antenna, the feed line, and the environment, okay? And where that dot is on the Smith chart will vary with frequency. And even across one band, you can get quite a little sweep across there. And if you pick like the middle of the band, the Smith chart can tell you how much capacitance and or impedance to add to get it down to a 1-to-1. Now, it's just easier to let your antenna tuner test that. Phase angle is important for a number of things, but for antenna work, it's just easier to understand that it's the reactance that will do that. Now, every antenna has two kinds of resistance. Ohmic resistance, which is the losses, the ohmic losses that come from heating either the transmission line or the antenna itself. Those are losses you don't want. On the other hand, you can, there's another kind of resistance, which is the equivalent resistance of the power that is radiated. So you want your radiation resistance to be much higher than your ohmic losses. This becomes an issue, like example for magnetic loop antennas, because the radiation resistance is so small, sometimes a fraction of an ohm, You want to get the ohmic impedance down to like a tenth of that. That's why people use pipe, copper strap, have these huge capacitors, and so on, is to keep the ohmic impedance well below the radiation resistance. With the dipole, you're mostly radiating, so not so much to worry about. Okay, let's go to the next chart. We'll do page down. Oh, we got to get this thing selected here. Every time I have a problem in my old age of not being able to use a mouse very well. Okay, this one is from Kenneth Coin. Thanks for this video. Oh, it's the video about my aircraft. I'm a new sport pilot with a flight design F2 light sport aircraft. Curiosity about radios in the aircraft led me to the ham radio hobby. There's an interesting overlap between the hobbies for people of like minds. I found a lot of pilots among ham radio operators, so that's really true. This one is from Francisco Lopez. Would it be okay for a halfway vertical to have a horizontal Yagi underneath it? Yeah. And what effects would the Yagi have on that vertical on top and vice versa? Would that Yagi act like a ground plane? No, it wouldn't. A Yagi's a Yagi, and it's usually designed for certain specific frequencies, for the ones us mere mortals can afford. It's, it's going to be 20 through 10, something like that. Now, you can put a vertical on top of that, a half wave, or just a regular vertical on top of that, for like 40 meters, 30 meters, 80 meters, and 60 meters, whatever. It seems to me counterproductive to go to the expense of putting up a big Yagi and then putting the Cushcraft R9 or something like that on top of that. I mean, you can do it, but then you've got two antennas for the same thing. The Yagi's going to be better. Now, it is true that if a signal is coming in off the side of the Yagi, the vertical might pick it up better. But the vertical will not tell you where it is. You have to swing the beam around to get to that. That is one of the drawbacks of a beam, is that you do have to aim it, and sometimes if you point it in the wrong direction, it can work against you. This was from ZZ. Okay, by the way, can you explain the velocity factor of wire, aluminum, and copper, etc.? It is vital to have when building antennas. Yes, it is true. This is from a video from a while back, number 809. Have you thought of a disc cone? Okay, I've drawn two lines down below. This spot right here is where you start, okay? Launch an RF wave into air or a vacuum, and it will travel at the speed of light. Now, there is a very slight difference between the speed of light in air and the speed of light in a vacuum. It's so small that us hams normally ignore it. Now, if you use just an ordinary piece of wire, like the wire in your antenna, okay, the speed of the electromagnetic field in wire is slower than an electromagnetic field in air or vacuum. It's slower by 5%. And so we say that the velocity factor of just plain wire, like for an antenna, is 95%. This is why we use the equation 468 over the frequency in megahertz to give us the length in feet of an entire dipole. That number, 468, takes into account the 95% velocity factor. If you're doing coax, some of the older coax, I think with the polyethylene in the middle, the old RG8, which is ancient stuff, and I don't think anybody uses it anymore because it's hard to work with. But it has a velocity factor of 66%. So if you put an electromagnetic wave into that coax, the wave will only get to here at the same time the direct wave gets out here. So these are times we're taking the same amount of time, okay? The electromagnetic field travels more slowly in a wire than it does in air or vacuum. Now that's real nice, but air or a vacuum won't connect you to your antenna. You have to have a transmission line, and the transmission line has a velocity factor. So it's the percent of distance that the electromagnetic field can travel in the medium compared to the distance that the electromagnetic field can travel in an air or a vacuum. So the velocity factor of light or F waves in air or vacuum is 100%. Okay, that's where we start at. So it's relative to that. Now, what travels in a wire? What travels in a wire? Well, it's AC. Travels back and forth and all that sort of thing. It's RF. It's an electromagnetic field. Now, electromagnetic fields have frequencies, and we say that the electromagnetic field is traveling in a composite direction, in this case toward the antenna. Okay, how far do electrons move in a wire? About an inch an hour, which is doggone fast when you consider you're at the molecular level. What is traveling in the wire that is important is an electromagnetic field. Remember that when we get outside of the radio itself, we are no longer using circuit theory to figure out what's going on, because it gives us an incomplete explanation. We use electromagnetic field theory, but we can cut that down to a few things that are of use to us as hams. And one of them is the velocity factor. It just helps cut things to the right length. Okay? M. Knoxman. When I was a wannabe ham in the early 80s, I'd listen to the 2-meter repeaters. A lot of the old timers would use Q codes on the 2-meter, 70-centimeter repeater just to show off they were code people. Mostly they'd use the repeater to tell their friends of contacts or have them join a net. I got my amateur radio operator license in the early 90s and moved to a new area. In the 2000s, quite a number of hams turned into Chads and got their knickers in a twist. Is he referring to like Karens or something? And think that using Q code outside of Morse code is a rule violation. It definitely is not a rule violation. They're very well understand. Today, as many hams on 6 meters and shorter have no code background, the knowledge of Q codes might be quite diminished. Maybe, but they're on the test. And there are common codes like QTH, QSL, QSO that are known. Well, they're not known much outside of ham radio. If you're going to be talking over link, like to emergency services, don't use Q codes, don't use 10 codes, don't use any codes. Use plain English, or if you're in Mexico, Spanish. You know, use the thing. I ran into a problem when I was trying to get some help for somebody, and I had very poor connection, and I was saying my QTHs. And the ham says, you've got to use the whole thing. My location is. Okay, because people outside of ham radio don't understand these. Now, the use of common Q codes is very common on HF phone, on single sideband. Very common. You don't hear very many of them, but you'll hear QTH and, you know, stuff like that. There's nothing wrong with that. It's ham jargon. Every hobby, every collection has its jargon. Certain words, common code phrases whatever to mean certain things, and there's nothing wrong with that. If you are a new ham, and like this guy right here from Quirky QRP has developed this little mat that you can put on your table that has some of the common Q codes, so you can look them up. By the way, when I was in the Air Force, I picked this up. So this is the late 70s. This is a complete list of Q codes, their meanings, official meanings, and also the Z codes. Now, the Z codes are used almost exclusively in the military, okay? And there is also a backwards reference. If you want to find the right code for something, they've got them by subject area. It's interesting that the R, S, and T codes, QR, QS, QT, those codes often refer to radio ops. And so they're used in the maritime circuits and so on. QTH in any language means what is, or QTH question mark, in any language means what is your location? Okay, and so on down the line. So there's nothing wrong with using them. If you're talking to a new ham, you would try to avoid using it. I know in the QST, which is a Q code by itself, QST is a general broadcast. The style guide for QST prohibits the use of Q codes in normal text. So I wouldn't say here at my QTH, I'd have to say here at my home location. I mean, we can't even use the code and then put the meaning in parentheses. And it is for understanding. If you are talking to somebody you're not sure understands, don't use them. You know, the whole point of communicating. And I would ask you to look at the transmit circuitry versus the receive circuitry in your radio. The transmitter's fairly simple. It's easy to blast a signal out. What's hard is receiving the signal. So you want to transmit the signal in such a way that it's easy to receive. So if there's any noise, any interference, any kind of a problem, please speak in plain language. Also, and this bugs me about youth, and not just today. When we were youth, we did the same thing. Youth love to speak as quickly as they can so they can get to the end of what they want to say so they can go back to their iPhone. You know, and when at church, when I've used youth in narration roles and stuff like that, I actually have to teach them to speak more slowly. Otherwise, they won't be understood. I had one adult once do a narration, and I thought I wouldn't have to do that, but he read through that thing so quickly it was obvious he was simply trying to get through it. And once you're done with that, you're going, okay, so what'd he say? You know, slow down, because the hard part of information transfer is receiving. Okay, so anyway, my thoughts on that. So let's go to the next one. Eric D. My father was in the Navy and stationed in Lakehurst in 1933. Lakehurst is in New Jersey, and that's where the big Zeppelin burst into flames and crashed. Was a radio operator with the Zulu Papa 12 Squadron, lighter than air, the Zeppelin, and he spoke of the Z codes that I just mentioned to you. And it was interesting hearing Dad recite those Z codes, a lost language in the ham radio communications world. They were never used in ham radio. They were used in the military a lot for CW communications. And they used them a lot to shorten those CW communications. But the ham radios always used the Q codes. The Q codes are an international standard again, but their primary use outside ham radio is in the marine world. I'm talking about commercial shipping. And now none of those people do Morse code anymore. They all do satellite communications, internet, and so on. In fact, Elon Musk's Skybeam system is trying hard to get into that market by simply putting an internet antenna on board every ship. Okay, good luck. Terence Barfield in the UK says, please tell me what actually is the RF coming out of the transistor. What is it made up of? Okay, I've seen this question before, and I've actually answered it a couple times. What's coming out of it is RF, radio frequency, AC. It's alternating current that is alternating so fast, it's in the radio frequency realm. And you can see the frequency of the carrier on the front of your radio. Now, the carrier is suppressed, of course, in single sideband. But what's coming out is AC at RF frequencies. Now, what is it really? Is it electrons moving? Not very much. I mean, they do move. But what now? You make the transition from an item that's built around mostly circuit theory, and now entering the world of transmission lines and antennas. And so once it gets into the transmission line, it really is an electromagnetic field. And the electromagnetic field in a coax stays entirely inside the coax as long as you've got 100% shield. Otherwise, it can leak. And that also means other things can leak in. But in wire, open wire transmission line or window line, the electric field actually surrounds the thing, which is why you can't just lay it on the ground or coil it up or something like that, because you've got different pieces of the electromagnetic field all coinciding with each other, and it creates a mess. Whereas coax, you can coil all you want, okay, because it doesn't matter. The electromagnetic field is entirely inside the coax. So what is it? It's AC at radio frequencies modulated with a signal. That's what's coming out. Now, when it enters the transmission line, it starts to behave a little differently. In the transmission line, the ratio of the voltage to the current, the AC voltage to the current, is the characteristic impedance of the transmission line. And the same is true in the antenna. Now, the antenna is spread out in such a way that each point on the antenna is like a little point that's radiating RF. Okay? And when you collect all those points together, they create a mess of RF. If you get a little further away from the antenna, about 1 or 2 wavelengths, all that mess superimposes on each other and creates a wave front. By the time you get very far away from an antenna, it's going out in circles around like this. Each circle is a shell inside, a sphere, I should say sphere, coming out as a sphere. Okay, and then your receiving antenna picks that up. That creates a little bit of a voltage on the coax in terms of microvolts. And that is amplified, gets the living daylights amplified out of it, filtered, all that sort of stuff, and you can hear what's going on. That's the magic of radio. So, okay, that's what's coming out of the transmitter. RF, radio frequency AC. Radio frequency AC. And, I mean, some of the old circuit theory things work, like you can put transformers in them. We often call those Ballons, or something like that, to change impedance if we want to. You can think of an antenna actually as a balanced device that changes the impedance of the RF from the 50 ohms in the cable to the 377 ohms of free space. Now that gets esoteric, okay, so we won't worry about that. Just remember, we are amateurs. We are not professional engineers. We're not college-trained RF engineers. We're amateurs. And we learn enough engineering so that we can do our job very well. Most of the major advances in antennas, transmission lines, etc., were made originally by hams. Okay, there was some stuff that came out of Bell Labs, but a lot of the antenna theory was put together by hams. So one of the purposes, the FCC official purpose, I mean, this is the not legislation, but regulation that allows us to exist as a service, is that we further the state of the radio art. So hams are constantly experimenting. The amateur radio publication that is the most technical is one that's available to you if you're an ARRL member by going to their magazines. It's QEX for experimental. And they're not afraid at all to throw calculus and stuff like that. The next most technical journal is QST. And then on the air, okay, is down kind of at a beginner level. And then there's the weekly ARRL newsletter that you should subscribe to that's strictly news. Okay, so that's what's coming out of it. Now, if that blows your mind, please simply allow your mind to be blown. In my opinion, a lot of what we do for amateur radio is just plain magic. What was it? One of the science fiction writers said that sufficiently advanced technology is indistinguishable from magic. Now this is KX4UL ham radio about my video about the J38 key. This is a key that was used extensively in World War II and is designed around a key that was actually put together in the late 1800s. And it solved a lot of problems. The shorting bar that you see right there is actually for landline telegraph, although a lot of hams just short it so they can use it to tune their radio. These things back here are used as part of an instruction program. The actual things that you attach to are here and here. Go check out the video, it'll show that. Okay, and KX4UL says he loves the look of the J38. It is the classic looking key. Has two of them, both are complete. I do two. I have a J38 and a JJ38. The JJ38 was made in Japan and actually has ball bearings instead of just pivots right here. And they are great keys. After the war, you could pick them up for $0.25 a piece or $5 for $1. Nowadays, $25 or so is probably a fair price to pay another ham for a completely working and intact key. Okay. Neil Gettig says, how much did your plane cost? Well, it's about to be for sale. It's getting all fixed up now, and the asking price is $45K. Want an airplane? There it is. I love it, but my wife insists I get rid of it, and I really do need to get the money out of it to pay off a debt that doesn't seem to get paid off otherwise. Okay, Charvester. Don't they make a coil inductor lightning protector? They may, for like AC, you know, your power coming in. And I've seen them, they're about this long. Now, the problem with coils in RF is it doesn't take much of a coil. It can be pretty small to block the RF. Okay. A few microhenries can block the RF. So we don't normally use them in there, except I know the Morgan ones have a coil in there somewhere that works together with other components so that surges get directed to ground. So look at the Morgan and the polyphasor lightning arresters. Now, both of those are DC blocking. So if you have a remote antenna tuner from MFJ that is normally controlled over the coax line, they put voltages and signals on there to do that. If you have that problem, you can go with Alpha Delta, or I think one of the two, Morgan, makes some now that have DC connectivity through it. Okay, so I have not seen coil inductor lightning protectors because the coils would either block or short the RF, but they are used in some devices. Okay, David Sandfenberg, TBH. I'm not sure what that means. I don't understand why people don't use a Ballon. You're saving literally a couple bucks, actually close to 100, but risking RF in the shack and all sorts of strangeness that comes with that. I cringe every time I see a dipole without a Ballon. I tell people, if you have RF in the shack, by all means, go put in a Ballon. Now, there are three types of Ballons: current Ballons, voltage Ballons, and choke Ballons. The first two are transformer type Ballons. The last one is just putting something that's high impedance, like ferrite, around the coax so that you can't get down the outside of the shield with the current. It just doesn't go there. It's got a high impedance. You don't want to short it because then you create a lot of heat and you lose that. That creates ohmic resistance. Okay, so I have never had good luck with Ballons at the center of a dipole. I just haven't. And a lot of dipoles that are sold commercially don't have Ballons there. If you do run into a problem, you can do a couple things. One is right at the feed point, loop about 9 inches in diameter, about 9 turns of coax, and just clump it together. And that acts as a common mode choke. It's an inductor. It acts as a common mode choke. Not the world's best, but it does. Or you can actually put that anywhere in the line, but probably want to get it right up at the antenna. The problem is that takes about 25 feet of coax. And so you're paying for that as coax. It's probably the cheapest Ballon. You can make your own Ballons. You want a 1-to-1 Ballon at the center of a dipole, but then you got to hang it there. It's heavy. And you got the coax coming off of it. You almost need a center support for the antenna to do that because of the weight. Mass in the wind, mass is the equivalent of inductance. So you can get a mechanical inductance. You can get a swinging in the thing, and it will actually at some point can break the whole antenna and bring it down if there's enough momentum. Remember, mass wants to keep going in one direction. It's sort of like inductance. The equivalent of capacitance in mechanical systems are springs. And the equivalent of resistance in mechanical systems is what's called the dashpot. It's actually friction. Okay, friction will dissipate energy and make something hot. And that's what resistance does. It dissipates energy and gets hot. Okay, so if you like the Ballons, use them by all means. But when I put up a dipole, I start out without a Ballon. Now, I know some people who put them up, they make them themselves, and they're actually choke Ballons. They're choke Ballons. They take a piece of plastic pipe, wrap a number of terms of RG8X around it, and so on, and it's a choke Ballon. Remember, a Ballon, balanced to unbalanced, is a function, not an architecture. You can create a choke Ballon to get the function of a Ballon, which is to separate the balanced from the unbalanced. Or you can do with the transformer configuration. Transformers by themselves like to be balanced. But there are ways of dealing with that to make one side unbalanced. So anyway, there we go with that. Steve C. says, get a stand, too wobbly. He's talking about the camera work we had there for a problem around, this is 556 AskDave, and we were having trouble. My assistant was trying to handhold the camera, and it didn't work. And as a result of comments just like this, when 556 first came out, we did go to a stand. So it's on a stand, and when we do the overhead, we go ahead and use the overhead camera up here rather than trying to hold a handheld camera over this. So we've made a change as the result of this. Okay, you can use ground in the building, but you need a substantial diode to prevent neutral ghost current backfeed on the ground terminal. I actually have never heard of that, and I'm sorry I didn't click on the read more there. And I think, oh, we've got one more here. Steve Genoway says, I've thrown 2 Nano VNAs in the garbage because batteries were about to explode. They run off of little lithium batteries. Now I have a Rig Expert Stick Pro antenna analyzer, works great. They do. I have a Rig Expert also. This is the tiny spectrum analyzer. You can get a Nano VNA in a similar box, but only from one source. See, the thing is that the actual hardware and software for these things is all open source. And so anybody can make it. But if you go to the original page for the people who are maintaining it, they say this is the United States source to go to for the official Nano VNA or tiny spectrum analyzer, okay? It's RNL Electronics, www.rnlrandall.com, okay? Go there to get your Nano VNA or tiny spectrum analyzer. They come with the right accessories. They're made properly. They use good batteries instead of something that will explode on you. So that's where you should go get these. I made the mistake when I got my Nano VNA of getting it from all people, Walmart. It was ordered online. They were selling anything at that point. But if you go to RNL, if they don't have it, they will allow you to place an order so that when it comes in, they'll ship it to you. It actually didn't. That's what I had to do with this, but I got it pretty quickly. Craig C., correct me if I'm wrong, but I think the CW counts as more points per contact on field day. 2 points versus 1 point. That could be a good reason to learn CW, or in my case, practice to get my speed up. By the way, getting on field day, you can very quickly get your speed up doing something like that, because the exchange is pretty predictable, okay, and you can do that. So yeah, you can get quite a few contacts. Plus you can consummate CW contacts a lot more quickly than you can a single sideband. And I think that is it. No. What type of flux do you use on the stainless part of the SO239 connector? Thank you very much for all your helpful information. Rosin Flux. There are two types of fluxes, acid and rosin. They both act to clean the item being soldered so that it won't tarnish while being soldered or something like that. Normal electronic solder, the kind you get, should have solder in it. But that's often not enough if you're soldering something big. So I have a small container of rosin solder, actually from Radio Shack. It's enough to last me a lifetime. And I use a little tiny toothpick to pick just a little bit of, kind of rub it over the container or over the connector like that, and then it solders much more quickly. So rosin, think rosin, not normal plumbing solder. Normal plumbing flux is acid core. Okay, you don't want to do that. Oops, I'm pushing the wrong button here. Donald Dodson says, you are the station net control. Name it what we want. After I was hacked, I renamed the channel to AskDave from David Kassler. And a lot of people search for David Kassler. Or if they see a video recommendation, it says from AskDave, not from David Kassler. So I changed the name of the channel after I recovered from the hack attack to David Kassler Ask Dave instead of just David Kassler. So either one works. Have I plugged the leak? Oh, man. I've been going around the dike, putting my finger in every hole I can find. I now have two-factor authentication set up for Google anything, and I'm putting it on other things like, banks, credit unions, brokers, stuff like that. Two-factor authentication, putting it on everything. I just purchased this key from Google. It's a Titan security key. However, it's Type-C USB, and my computer doesn't have that. So I've ordered. It was supposed to come with an adapter, but it didn't. So I ordered one from Amazon. Should be here in a couple of days, so I can use that as a backup. And that is clearly something that nobody else can have. Now, is that going to make things perfect? No, it is not. But it certainly makes it better. And I appreciate everyone who jumped in to offer suggestions, help, who stuck with me. I lost quite a few subscribers during the period that the hacker was showing these stupid visuals about crypto. It was set in a studio where a supposed journalist was asking a supposed expert about crypto. And the guy sang the praises of crypto over and over and over again in a beautiful professional set. And that's all they showed was that. And fortunately, I got a call from the ARRL, from Steve Goodman, who handles all the relationships with all the YouTubers. He's a YouTuber himself. And he told me about the same time I noticed that it was hacked, but he also told me how someone else he knew got hacked in exactly the same way and knew what to do. And so working with him around the loop, I finally got connected up to YouTube, and they stopped this, and we had to go through a terrible procedure to get everything back. Now, one of the things that was hard was the hackers marked all my videos private. Now, I've got close to 2,000 videos. There is a way you can mark every video and say change the visibility to public. But that only did about half of them. So I literally had to go down page by page and make videos public. And one of the problems was that on some of them, it didn't keep the original date of publication. It republished the video. So that's why you all got notifications and you look in there and you saw some of the older videos that are years old have popped up as new. Go ahead and watch them. I need the views. So the subscriber count has turned around, starting to go back up. I really appreciate that. If you're watching this and you're not a subscriber, please subscribe. If you'd like to help support the channel financially, the best way to do it is on Patreon. Go to patreon.com/KE0OG and pick a tier that works for you. There's 4. $2 a month, 5, 10, and 20. People tend to be about equally between the $2 and 5. And there's a few 10s and a few 20s in there. You do whatever you want. Now, remember, this is free information. If you don't want to support the channel financially, at least please support me by subscribing and clicking on like. It will not cost you a thing, but it will help YouTube know that this is a channel worth recommending. As you can see up directly above my head here, I've got my 100,000 subscriber plaque, but there aren't a million hams in the U.S., so I doubt I'll ever get to 1 million, but I'm at about 120,000 right now. Okay, so there you have it. Until we next meet, 73.